bunch of pixels, you can have each pixel be a value, a scalar value, or a vector. So if we are doing a grayscale image, you might have intensity values. So a pixel that is totally white might just be 0. And a pixel that's totally black could be like 255. And then in between, you have scales of gray. And if you want to do a colored pixel instead of a grayscale pixel, you might represent it as a vector of red, green, blue values. So you have the intensity of red, intensity of green, and intensity of blue. And then you overlay those 3 intensities and you get some color.
Great.
So, being as we can represent pixels as vectors, we can take linear combinations of pixels. And here we can actually take a linear combination to combine these pixels, being that the proportions we're taking add up to 1. 1/3 plus 1/4 plus 5/12 equals 1. We end up with this, just multiply these numbers by 1/4. So that's how we can take linear combinations of pixels. Let's talk about. So if we want to represent an entire picture, if the picture is grayscale, we can set up a matrix of scalars, and maybe we'll just have a bunch of grayscale values corresponding to the image. Let's say it's a 4x4 image. So this image represents the 16 pixels of the grayscale image, but if we want it to be a color image, we actually need to make a matrix of vectors. Red, green, blue vectors. So imagine that we have this 3x3 grayscale image represented as a matrix. We can actually manipulate it with matrix multiplication. And the simplest operation would be to just multiply it by the identity matrix. And multiplying an image by the identity matrix simply yields the image again. But if we want to start blurring, then let's say perhaps I want to blur the middle row with its neighbors equally. So I can modify our multiplication matrix to reach across the rows. So for the middle, we're actually going to take 1/3 of the top row, 1/3 of the middle itself, 1/3 of the bottom row. In this matrix multiplication, you'll end up with the top row and the bottom row remaining the same, but the middle row will be blended with the values of the top and the bottom. So I don't want to do the entire multiplication, but if we just try to derive what the value in the second row, first column would be in this blur, you'd have 1/3 of 1, 1/3 of 75, and 1/3 of 93, which gives us our familiar averaging formula, where you sum the elements and divide by the number of elements. And the result would be 169/3. Yeah, I think that's already in reduced form. So if we make out just the first column of the result of this multiplication, you'd have 169/3, if I'm correct, and 93. And you can see how by reaching across the rows, we've averaged the middle pixel with the rows above and below it. So that's great if I want to take an average across all 3, but what if I want to emphasize the middle a little more than the others? I can actually change the weights that we're using so they only take, 1/4 from the row above, 1/4 from the row below and 1/2 from the row itself. Well, then our middle pixel here will be 1/4 of 1 plus 1/4 of 93 plus 75/2. So we can see over here that we more emphasize the value itself versus its neighbors. This is called a weighted blur. So the result we get is this weighted blur matrix. Now, if we look at all three matrices, starting with our original image, 75, 72, 87, the average blur ends up somewhere close to their original values, 75 to 56, 72 to 61, 87 to 90. But the weighted blur is closer to the original values because we weighted the original row more heavily. 61 is closer to 75 than 56 is, 63 is closer to 72 than 61 is, and 89.5 is closer to 87 than 90.3 is.
So this here is called a kernel. This is basically just the blurring matrix that you would apply to a different matrix. So right here, would be the actual image matrix. So obviously, since it's a 3x3, we would need a 3x3 blurring kernel. This is basically just like a box average kernel because it's 1/9 all around. And as you can see here, there's 9 different numbers. So you just take the average of them. And then once you actually calculate it out, okay, this value right here, it worked out really nice because we got full columns that are the same number. But basically, this is just another way to apply a blur-based function.
Hi, I'm going to cover neighbor-based blurring using zero padding and circular padding. So if we start with a matrix A and we use zero padding, that means basically these outside values that would make up the larger matrix are all zeros, and we would just not include them in the averaging for the value. So for example, if you want to transform this value in the new matrix, we'd be using 2 and 4, and for this value we'd be using 1, 5, and 3. So for example, to calculate this new value in the new matrix, it'd be 2 plus 4 over 2, so 6 over 3, 2. Would be 3, that's the values, and that would be the transform matrix. I was covering zero padding, but in this one we want to use circular padding. So if we try to do circular padding, we want to basically move this edge around to the other side to make a larger matrix. So if you look here, for this, if you make a circular padded matrix, we want to move this 3 over to this side, which is what's shown here. And if we want to do it to this side, so 1 would move to this side, and so on for the rest of the values. And this way, every pixel in the matrix will have 4 neighbors, 1 on top, 1 to the right, 1 to the left, and 1 to the bottom. And if we transform the value, for example, if we do it for 1, it'd be 2 plus 7 plus 3 plus 4 all over 4 to give you 16 over 4, which is 4 right here. And you do this for the rest of the values to get your transform matrix, and that's circular padding.
So this is a vectorization. It's really simple. You kind of go left to right. This column stacks, and then on top of this column, and then those stack on top of this. So literally, you would take that first column, put it in a column. You take the second column, put it below that column to make it longer, and then you just stack it. This was the original vectorization that we computed from the original matrix. Now to get a blur of that original matrix, we can use the vectorized matrix and multiply it by this chart that shows how to average each element. So for example, this 2 only has one neighbor, so there's 2 elements total, and to take the average of 2, it's 1/2. So you would take 1/2 of 2 plus 1/2 of 20, and you'll do that for each element of the vectorized matrix to get these values. And then obviously when you do the reverse of the vectorization, you would bring these numbers over here to take back now a blurred version of the original matrix.